Yeah, maybe we can start. Welcome everyone. And today we are happy to have a talk by Riccardo Gonzo, and the talk is going to be about gravitational bound waveforms and amplitudes. So please, you can start.
Yeah, so thanks for the invitation. Let me start by saying, please stop me at any point for questions. I have a lot of slides, but I'll try to go through more introductory part first. So I'm trying to explain why we want to compute these waveforms, why I think that particle physics tools are interesting and useful for this. So that's kind of the outline of the talk. So the first part will be reviewing this kind of post-Minkowski expansion, essentially expansion in the coupling, just like in gauge theory, and how to derive classical scattering amplitudes. And I'll try to be pedagogical as much as possible for this. And the idea is to try to derive an expression for the waveform for classical two bodies that are kind of modeling compact binary spirals, I will see. These techniques are usually adapted for scattering states, but we want to try to understand how to attack the bound state problem from at least at the classical level, and we see this is possible. So I'll use a tool which is called classical Wavell-Salpeter equation. I'll describe that, and then I'll try to say how we can derive indeed bound waveforms, which is one of those robots we're interested in from the scattering waveform. Okay, so I think one of the interesting parts of the actual time we live right now is that gravitational waves were discovered very recently, and this calls really for new analytical techniques to study a two-body problem. And this is really, I think, the best time to look at this, knowing that we have seen already over 100 events, and we see much more in the future. Of course, we need what we need is some templates to extract the signal. Otherwise, just hidden behind the noise, essentially. And so it's very important to have analytical data for this. There are three kind of stages of the evolution of a compact binary system. You can think about black holes or neutron stars. So one is the spiral, which I'm mostly interested in because the objects are far apart. So you can use effective field theory tools to study the long range interactions using particle theory techniques, as we'll see. Then there is the merger part, where more numerical methods are used. And then there is the ring down, when you still can use perturbation theory on top of a background. And you're supposed to put all these techniques together. So various techniques for different stages of evolution of the binary are supposed to be together. And there are two kind of main methods to do this. One is the effective one-body, and one is the self-force approach. For what I'll say today, I'll only focus on the spiral phase. Indeed, we're using amplitudes, so particle kind of tools. And we can model, in this first stage of evolution of binary, compact objects, point particles. And the idea essentially goes back to effective field theory, essentially. So I would like to give a quick dictionary how things will work. So if you, in the real world, you have a compact object of mass m, and here I'm thinking about really, black hole or neutron stars. From the effective field theory perspective, is a point particle of mass m. Then you have some spin effects of some magnitudes. This correspond in some way to some spinning particle of some classical spin. If you want tidal effects, which are very important to understand, for example, neutron star deformation, or you want a GR curvature correction, so a deviation from GR, this can be encoded into higher dimensional operators. And you can also have absorption, and here you need some non-unit absorption degrees of freedom. Also, Alex is in the talk have developed some of those, for the spinning case and the absorption case. But today we'll focus only on the first line. So our compact object mass m will correspond to point particle of mass m. I'll say something about spin as well, but mostly it will be on the first line. So why amplitudes? You can ask, these are tools that are applied to scattering orbits and not bound orbits. But the thing is that this encodes in a nice way the gauge they're invariant objects that encode in a nice way, like perturbation theory of point particles. So they give a very compact analytical results, and that's what we want. We want something compact analytic and hopefully useful, as I said, to understand at least the inspiral phase of the two-body problem. So one also big motivation is that we know LIS has been approved a month and something ago, like I think late January. And we know, I mean, we're going to have, now we have hundreds of events. We're going to have thousands. And the type of waves we're going to use are going to be much more precise in a different frequency band. And so as theoretical physicists, I think we need to work hard to be ready for 2035, which is expected date. Hopefully it will be that. So I think it is, as I said, an exciting time to think about these kind of questions with a new kind of perspective. Okay, so what we start? So we want to describe a state of two particles. And so we kind of take this state as two massive particle state is P1 and P2, smeared with some wave packets. So wave functions psi1 and psi2. You have to think that these wave packets being some kind of WKB wave packets localized on classical trajectories. And you want also to have them, these wave packets, like shifted with this impact parameter B, which appears here in the exponent, which essentially is the classical impact parameter will be. And essentially some length scale that is associated to the exchange to the exchange between the two particles, essentially exchange of magnitude to the two particles. Because we want, I'll discuss this later, why this is important for the effective field theory approach. So dynamics of evolution is just determined by the standard minimally coupled theory of matter with GR. So you just take a scalar field. As I said, at the moment, I have no spin, no dimension operators. And we perform a perturbative expansion. The important thing to understand here is that we expand also the metric. So the metric is going to be the flat metric plus your perturbation theory H mu nu with some coupling kappa. And this is called post-Minkowskian expansion. Okay, so this expansion captures the expansion in the Newton constant. And you can take, your favorite metric, for example, Schwarzschild, and expand in G. You see there is a non-trivial, non-perturbative series. And this is recovered, for example, by the diagrams like the one in the bottom here. So a 3-point coupling of a massive particle with a gravitational. If you take expectation values, you can compute. It's not on shell, but you can compute like expectation value. It will give you the linearized term in the Schwarzschild metric. Okay, so this is the kind of idea. These terms like will reproduce dynamics of the black holes when you look at large distances, as I'm going to argue soon. So how we compute classical observables, just like in quantum mechanics, you take expectation value. So expectation value between the states, you evolve your states. So you have a time evolution operator, your S matrix. You evolve the state, the expectation value in the final state. So your final state is S times psi in, okay? You expand your S matrix into a disconnected part and an amplitude, non-trivial amplitude part. Okay, and what you get, this is kind of in formalism. So what you get a term linear in the amplitude and a term quadratic in the amplitude. So, and in particular, this involves different epsilon prescription. You might be familiar with the Feynman epsilon prescription, which is what I indicate with plus here, but you will get also term with the minus epsilon in general, also term involving the cuts, so plus and minus. For who is familiar with the Swinger-Keldysh basis, exactly what is happening. We're just taking some classical kind of on-share reduction of that. So this is a general philosophy, but we're going to go into details for the applications. So how do we take the classical limits for the scattering of point particle? So essentially, also please tell me if you have any questions, like as I said. Essentially, we want this wave function, right? So remember, you have a two particle states, which we have over here. And then we want to consider some wave function localized on classical trajectory. So this has been described in this nice came-up paper, where essentially what you use, is, as I said, is some kind of WKB type wave function, which where your momenta of your particle is actually localized on some velocity u. So and here you have various quantities. So you have the Compton wavelength, which is some essentially the size of quantum effects. And this is this LC. You have this LW, which is the spread of the wave function, which captures kind of finite size effects. And then you have this parameter. As I said, like it's some large, some length that you put in the system because you want the system to describe it with a long wavelength separation. Okay, so the exchange of the gravitons, so gravitational waves, must be soft, must be in spiral phase. So you need like this parameter to be very large. This is the kind of the conjugate variable to the transfer of the momenta. And this must be larger than, in particular, the spread wave function, because you want like to have your wave packet as your wave function as a point particle, essentially localized as a point particle, but you want still like the spread wave function to be larger than the Compton wavelength. So quantum effects must be suppressed. Okay, so the Compton wavelength must be the smaller object, and that is the kind of expansion you're trying to take. So for massless particle, you can use coherent states. I'm not going to talk much about that, but I just want to point out you have a nice description, classical level, both of massive and massless particles. I'll just give a kind of one-line example, like of what it means to take the classical limit, because people are very familiar with things like saddle point of the action, the path integral, and here things are slightly different. In particular, not only in general three-level diagrams contribute, but also loop-level diagrams. So one of the things that we want to achieve is that we want like, so you see here a three-level diagram, right, with exchange of a graviton. So this straight line are the two massive particles I'm talking about, okay, this diagram over here. They exchange some momentum q mu. What you want is that this graviton must be soft, okay? And like when you have the Planck law, so you think about the Planck spectrum, when you recover the classical limit, you have to send h bar to 0. So you have E equal h bar nu, right, your frequency, and you want to send h bar to 0. Here is the same thing, just applied to every massless momenta, okay? So in particular, the momentum on the graviton here is massless, and so you want it to have this large separation in position space. This Q is conjugate to the input parameter, so you want to rescale like h bar. This limit at 4 points is essentially equivalent to iconal, Regge, this kind of names, okay? The literature Regge limit, iconal limit is essentially the same thing. The reason is that at the level of the T, T is the Mandelstam invariant, just as the difference between P1 and P2. It's, sorry, P1 and P1 prime. This one is much smaller than the center of mass energy. So essentially, the expansion h bar going to 0 is essentially the Regge limit, where t is minus t is much less than s. Okay, so the same procedure can be applied to higher point amplitudes. Essentially, you still rescale like your exchange momenta. So here you will have more than one exchange. So for each particle, you define some q, p1 minus p1 prime, and for each one you scale by h bar. And the same thing for also the external emission, okay, or external graviton. And so this is very important, as I said, because you want to recover the soft approximation where you can trust your low energy theory, okay, of gravity. So you don't need anything like string theory here, exactly because you are in this regime in which these gravitons are all soft. So the lessons here is that only wave vectors are classical, and we need to restore h bar. So this is the kind of philosophy. And of course, you can use also other alternative like classical physics tools like wordline approach, for example. This is going to be equivalent, okay, to the amplitude approach, but I'm going to stick with the amplitudes for this talk. Okay, so any questions up to this point? That was kind of the introductory part, mostly. I have still some to do, but
can I ask a question?
Yeah.
It seems to be very complicated to solve the quantum problem and then send h bar to 0. Is it easier? Namely, it's easier probably to solve the classical system from the start. So why is it
Yeah, good.
not easier?
Yeah, good question. So, well, one thing that is quantum mechanics is unitarity of the S matrix, which is not usually present in a classical context. And also, you have like the S matrix has a lot of analytical properties, like the factorization, poles, and all the structure, which is misstudied, non-perturbative as well. And I'll show one example later, like for the spin waveform. But essentially like there are a lot of constraints in the quantum theory which are not there in the classical theory. And because of this, some calculations are going to be easier. And that's the reason why some of these methods actually overcome traditional general relativity methods, at least in this limit, which is essentially a large intrinsic limit, like of the two-body problem. So this is one of the reasons. So the constraints in the quantum theory, like unitarity and analyticity, like are really helping with this calculation to push it forward to higher order. There was also a paper today at 5 p.m., for example.
Is it just that you're saying that we know quantum theory just very well, and we don't know classical gravity well enough to guess from the beginning the analytical properties of the solutions, the analog of the unitarity of S matrix, classical now?
Well, essentially, I mean, it's more than we understand much better the properties, like, as I said, the unitarity, analyticity, factorization in the quantum theory than the classical theory, and they're not so much well developed like within the classical setup. So things like unitarity, cutting lines, and putting them together, things that have been developed in the past 20, 30 years, like for collider physics. And these tools have never been shown up in the classical theory. And this is why, I mean, some of the results that now we got in the community are very new compared to, what is known in the classical GR setup. So I think it's, especially for analytical, if you're interested in analytical approach, this can give some new insights, at the least. Yeah.
Thank you.
And if you think about effective one-body or self-force, like these things, at some point they go numerical. And here you have some systematic way of understanding things. Of course, it has some issues, as I will describe, but I think it's really a different approach, and I can give something interesting. So, okay. Other questions before move forward?
Yeah, can I also ask something?
Yeah.
So do I understand correctly that this limit is classical in the sense that, so here for this amplitude on the external lines, you have some sort of, let's say, one particle quantum states, and in the limit you replace them by classical point particles, essentially.
That's right, yeah.
So I'm wondering, I know maybe it's kind of too silly, but can you do that some kind of a limit like that, but at the level of action?
Yeah, you can do. I mean, basically, I think the word line is the closest to what you're asking. So you can treat the point particle as word line in a word line approach, and trying to recover the word line partition function from the field theory partition function. That's probably what you're kind of asking, in some sense, if I understood correctly. So you're saying at the level of the action. Sure, you can use the equation of motion at the level of the action and try to use this, this effective field theory power counting, essentially.
Okay, thank you.
You need to plug back the equation of motion inside the action and solve it perturbatively, order by order, with this kind of power count. Okay.
Yeah, okay, but then it's some sort of still scattering observable. It's not exactly at the level of action, right?
Then it's still some scattering.
Scattering observable in the sense you solve equations of motion perturbatively.
No. I solve and I plug back into the action. I have an action which depends on x and x dot, some trajectory. I solve perturbatively and I plug in back into the action, order by order in perturbation theory. And I correct the action order by order.
Yeah, but by doing this, you compute some sort of scattering observable, right? It's not that.
Yeah, okay. So in some sense, yes. Yes, in some sense, yes. Okay, fine. Yeah.
Okay, thank you.
Oh, you're welcome. Yeah, thanks for the questions. Okay, so how is the waveform derived? So essentially, what is the waveform? So at least the linearized waveform, the one that everyone is studying and using for this templates, is the expectation value of the Gravitational operator. So you do this in expectation value, you put the h mu, your field operator, you expand in modes, okay, just you do in the standard field theory, you expand in modes. And what you get, like when you act on the two particle states, you create like two particle states plus a graviton, at least a leading order. So it's not surprised that the leading contribution is a 5-point amplitude, where you have the two massive particles coming in, the two particles coming out, and a graviton coming out. Of course, there is a lot of integration over here. integral over phase space, and integral over wave functions. But the interesting part is now, as I was saying, unitarity and analyticity place a lot of constraints on the quantum theory that here you can solve actually the for a 3-level answer, as we'll discuss soon. Before doing that, like, let's look at, so here you see you have a true real part, okay, of 5 points. So it will be the amplitude plus the conjugate. As I said, there is a play of high epsilon prescription. What has to happen in a classical limit is that you only have retarded propagator. So retarded physics is the only one we care. You put a condition in the past, you evolve in the future with retarded physics, a retarded boundary condition. So what happens is that you have to combine the two exponential in these limits at large distances. And what happens, you recover the retarded propagator by combining the two exponential and the conjugate, okay, from the real part. And in particular, you find this nice expression like of the waveform, which is essentially a function of the source. So this J tilde, you have to think of this as like the stress tensor of the two binaries, okay? If you want to think about it, something like that. And the stress tensor of the two binaries, contracted with epsilon mu, okay, is related to the 5-point amplitude at least 3 level. And here you have some measure of integration, okay? So what you want to do, you see in red, like these are all the measure integration you have to solve, you need to integrate, like to get your time domain waveform, okay, your H. So our goal now is to try to see, like, can we, you know, is there a nice method like to integrate this 5-point amplitude, like to get the waveform? So one nice way is use on shell tools. So we can simplify the phase space integration of the 5-point amplitude using the symmetric analyticity unitarity. I'm not going to go into the detail, but essentially at 3 level, the amplitudes are only rational with poles. And because of this, they have very simple analytical properties. So in particular, this phase space integration over here, so one of them is solved by this momentum conservation, okay? So this is D4Q1, D4Q2, and then the omega. So D4Q2, for example, is solved by momentum conservation. Then you have another 5 integration variables. So you have 2 delta functions, so you remain with 3. I'm just going to give you a short version of the story. Then you remain with 3 integration, right? D omega, and then 2 of the integration left over for one of the D4Q1. So what happens is that because the 3-level answer is, as I said, the special analytic properties, you can solve this integration by going to complex plane and pick up the poles. And these poles correspond to factorization. And the nice thing is that you get a very compact answer for the 3-level waveform. This is the spinless case. We actually computed the spinning one as well, 3-level. And it matches all the results by Kovacs and Thorne. So this is a kind of, if you look at their paper in the 80s, is very long with a lot, many pages of calculation. Now, these tools are making it much compact. They give a much more compact result. And which is also gauge invariant. You can decide here which frame you choose, and I think it's just much nicer. So as you see, it fits in 4 lines essentially compared to the few pages of the original paper. Of course, we went much beyond that Kovacs and Thorne paper, but I just want to point out that we compare with the literature like NGR, and that gives the same results. Okay. Okay, so what's the 3-level scattering waveform? If you go to equatorial plane, it looks like this. So essentially a jump, some kind of step function. It's not exactly, of course, a phase function, it's more complicated. Here I also restrict to equatorial plane, otherwise you have some imaginary part. Most of the energy is released during the periastron. So you have the closed approach, that's the time you release most of the energy, which is correspond to the jump. So this is, you know, very different on what you expect to the waveform I showed before, that is oscillating quasi-periodic but perhaps it's possible to establish connection anyway, and as we'll see, this turns out to be the case. So it's quite surprising, but even from a waveform like this, you can learn a lot from the bound state physics, as I will try to discuss later. Okay. So we want now to connect this. This is a scattering observable, okay? Scattering waveform, 3-level scattering waveform. We want now to connect with bound states. So the interesting idea is that, okay, so you have some scattering, so it corresponds to some kind of hyperbolic motion, okay? Which is here on the left. And somehow you want to turn it into something like bound, some ellipse, okay, which is the type of relative kind of trajectory between two bodies if you study, for example, Newtonian, post-Newtonian dynamics. And the idea is to try to use the analytic properties like of your answer, your observables, in terms of this binding energy, essentially the energy minus the sum of the masses, which is above 0 for scattering orbits and below 0 for bound orbits. We actually use this P infinity, which is related to the rapidity. It's a slight different quantity, is much more useful because it has it appears directly in the observables in a more interesting way. But they are all related. So it's all, when I talk about P infinity, it's talking about the energy, okay? There's a direct relation between the two. So there are, I would say, two powerful methods to extract bound state physics for amplitudes. The first idea is that when you do scattering, you have some kind of potential. So you are, exchanging your particles like the three-level amplitude I showed before. So you are exchanging your graviton, and you can extract, for example, in the center of mass frame or in any frame, some potential to add your Hamiltonian. So perturbative order by order, you can try to extract some Hamiltonian. And Hamiltonians, if they, let's say, unless they depend on, in the history of the trajectory, which happens at various orders, but they vary for arbitrary orbits. Where an Hamiltonian is the same for scattering and bound. You just add the equation of motion, you put different boundary conditions, okay? But the other idea is to have some kind of imaging variant map from observable for scattering and observable for bound. And here I add some parameters that can be angular momentum, tidal effects, spin, and masses, okay? And the interesting part that this is also motivated by some pure bound state approach, which is this Bethe-Salpeter equation, which I try to describe. So yeah, these are the current two methods that try to derive, bound state physics from amplitudes. They both suffer of the same problems at the end. So, I mean, basically, none of them is really much better than the other, I would say. I'm going to focus on the second one, okay? Any questions up to this? Even basic questions, like I'm happy to, in case. Okay, go on. Okay, so I'm going to go something very simple. Which I hope like it's very familiar to all of you, which is like the Coulomb problem, essentially. Coulomb problem in gravity, which correspond to linearized Schwarzschild background. So what you can do, you can take your usual Hamiltonian, okay, and you can try to solve H psi equal E psi, the usual Hamiltonian problem of the eigenstates, and you just put a linearized Schwarzschild background, which is this kind of linear in G, you see. So it is kind of potential, which is linear in G, 1 over R. It's a bit more complicated, is the energy dependent, like compared to Coulomb, but essentially it can be mapped exactly into Coulomb. So you solve really the eigenvalue problem, and you can solve it, now it's Coulomb, you can solve it for bound and unbound, right? So you can try to see if there is a relation. So this is a very basic question. So if the energy is above this is mass of the particle, so you can impose scattering plane wave boundary condition, then you get a continuous spectrum, which is the scattering case. So if you have energy less than the mass, you get some normalizable wave function. So you want some fully normalized wave function, and then you get some discrete spectrum. And somehow these two things are connected because this, as I said, there is the same Hamiltonian. So somehow these two things are connected. And I will try to discuss that in a classical limit again, like so the question is, what is the relation, if there is a relation between scattering and bound wave functions for Coulomb problem? And the answer is not so easy. And the reason why it's not easy is that usually scattering is a sum of partial waves. So if you study the scattering problem, you get a sum over spherical harmonics times the partial waves coefficients. Whereas with the bound state problem, when you solve the bound state, it's already labeled by the quantum numbers. So the scattering one has a sum of all these essentially partial wave coefficients. And what you find actually, if you look at the scattering case, you see you have a pole, you have gamma functions, poles and negative integers. And these poles correspond to kind of actually resonances, and therefore when you analytically continue, like bound states essentially. So what we found is that what you need to do is essentially taking the residue on the pole. So residue on the pole will give you exactly at the level of the partial wave. So you first decompose your scattering with function in the partial wave basis. So we'll see what this corresponds to the level of amplitudes later, but just to remind that the partial wave basis is very critical for this to happen. And then you have some residue to take. So you want the residue at the bound state pole to give a relation. And then you have a simple relation like this, where this y is essentially a dot product between the two velocity, okay? Is the rapidity, if you want. And it's written like this. So for this simple case in the probability is just the energy over the mass, okay? So as I said before, if it's above 1 or below 1, it determines whether the system is bound or unbound. So you see there is an analytic continuation of this square root, okay, which goes from the scattering case to the bound case. And there is a residue, okay? So in terms of this P infinity variable that I was talking about, it's just energy, okay, in different variables. When you binding energy essentially in different variables, then you find this expression. And the question you want to ask is, can we simplify the map? Why? Because we have a residue here, and
sorry, what is x? Could you remind us what x is?
Just the position, yeah, position.
But you have r as well, a vector r.
What is r? Sorry.
Well, in the argument of the f1 f1, you have r.
Yeah, it's the modulus of x. Sorry, yeah.
And a vector r as well you have there.
And also vector r, yeah, should be x probably. Yeah, thank you. Should probably x yeah. It's equivalent. Yeah, it's x bold x. Yeah, thank you.
So x is the three-dimensional
exactly.
position.
Yeah.
Variable, the same as r vector.
Yeah, the same as r vector.
Oh, okay. Thanks.
X vector and r vector are the same. Yeah. Yeah. Thanks for the question. Yeah, should be more clear about this. Okay, so basically, we find this other question, first of all, on this slide. I hope at least this is, the Coulomb problem, I will kind of clarify this before we go to the full waveform, but yeah.
So once again, so these two wave functions are just eigen functions of energy, right? Just in different cases.
Exactly. Exactly. It's just solving h psi equal e psi. Yeah.
Okay, thank you.
So it's really plain that, like, just that. So there is a residue involved. That's what I'm so okay. So once it's accepted, I mean, this formulation is nice, but I mean, it's Coulomb problem. It's problem. It is a lot of simplification, for the linear Schwarzschild. So we want to go to the full case. And is there also simplification that maybe doesn't involve this residue? And the answer is yes, and it's quite interesting. So in perturbation theory, like this bound state pole where we take this residue, right, is generated by iteration of potential. So essentially, you see the iteration. So here you have the potential, which is your linearized Schwarzschild potential, for example. And I just do perturbation theory. So order G square, and whatever. And I will sum all this, right? The solution I get was non-perturbative. But in some sense, only the potential itself, so only the first diagram should be relevant. The other should be just iteration. So essentially, all the physics must be encoded in the first diagram in some sense, and that's the key. Like to try to kind of extend this map like to the waveform as I discussed. So the natural generalization of the picture is that essentially you have the non-relativistic two-body problem, and what the source here, your potential of Schwarzschild generated by another particle. So you get some ladder type approximation. And this is true in non-relativistic limits. When you go to the relativistic case, it's more complicated, but essentially still an amplitude recursion relation. So you have some kernel, which is your 3-level, and you iterate it, okay? And this is essentially exactly equivalent to Swinger-Dyson equation, but you need to truncate the Swinger-Dyson equation to two bodies, okay? So you want to take like the kind of two massive particle version of the Swinger-Dyson equation for the two-body problem, and you get an amplitude recursion relation after you do LZ reduction. And this is the recursion relation. So in a sense, what we are saying is that all the physics is encoded in the kernel, okay? So in this kernel was this one before. And this hopefully will simplify the map because the residue that we had to take is just generated by this iteration of potential. So, and as I said, like this is kind of called Bethe-Sapir equation. So essentially an iteration of the 4-point amplitude kernel, and then the convolution of the kernel with the two-body propagator. And kind of nice that it was invented by one particle physicist, Bethe, and then Edwin Salpeter, which is actually an astrophysicist. So we want now to solve these things in a classical limit. We think that it's possible because essentially we know the Icona resummation is possible to get some kind of iconal phase. And this is kind of the analog of that, okay, in this framework. Essentially just saying that you have some massive particle reducible object, which is this kernel, which is just reproducing for you all the physics. And so how to do that? So essentially, I give a quick version of that. What we get is, you can just look at the picture. Essentially, you still get the first term is your classical kernel. So you take a 4-point amplitude, you do the limit you take before that I was telling you on the amplitude. Okay, h bar going to 0. And for the recursion, that will simplify dramatically. Essentially, the two-body propagator gets replaced by the on-shell version. So two delta functions here. And these are very similar to the one appearing, for example, in the word line formalism. It's just telling you that the particle are on shell. If this PA was in the rest frame, it's just conservation of energy, okay? The fact that these are delta functions, there is also some M. This M is the number of two massive particle reducible diagrams. It's some grading of the new recursion relation. And essentially, if these are delta functions, you can solve this recursion relation. Because this delta function is D4L, you have two delta function, D2L, and then you see you have L and Q minus L. So this is essentially a Fourier transform of a convolution. It's a convolution, and the convolution can always be solved by Fourier transform because in the conjugate space there will always be products, and that's exactly what we do. We go to this conjugate space, there is imparameter space, which is essentially just a Fourier transform of your amplitude. So you take your amplitude in Q, okay, it's function of this change, and you Fourier transform in the conjugate space. It is E Q dot B. As I was saying, it is the relevant parameter B, which is conjugate to the transfer of momenta. And what happens is that this simply becomes a recursion relation you can solve. And it's nothing else, if you want, than the Icona resummation. It's just shown in terms of this solution Swinger-Dyson equation at two massive particle reducible diagrams. There's a natural generalization for spinning particles, which I'm not going to talk about, but it's also possible to do. So you see your amplitude, okay? So you have to do a Fourier transform in Q. So from Q you go to B, and then at that point that's just exponential. So it's the exponential of this kernel in the conjugate space -1. And the interesting part is that the analytic structure, in particular, poles arise completely from the Fourier transform. So this is quite interesting because, you know, things like when people do study asymmetric bootstrap approach, they study bound states, and these, you know, are non-perturbative objects in some sense. And here they just arise from this convolution. So once you have the kernel, you can just carry on and do this Fourier integral and get your amplitude in the normal momentum space. Okay, so I'll give you one example. So this is one example up to 2 p.m. So this is like 3-level exchange and 1 loop diagrams. And this encodes the conservative dynamics up to 1 loop, okay? So G square. So you see you get 2 contributions. So one contribution in G, one in G square. And they are function of this rapidity that I was saying before, essentially the binding energy and the masses. So an interesting part is that the motion is actually restricted to a plane. Why is it to a plane? Because everything determined by the conserved quantities, the binding energy and the angular momentum. Okay, so it's spinless particle on a plane because by symmetry, if you want. And the interesting part, you can rewrite your kernel in terms of conserved quantities. So why it is useful? Because as I said, you want to go to unbound. So you want to kind of go for the binding energy to be above 0 to below 0. Okay, so if you have an analytic function of those quantities, you can try to analytically continue that. And that's exactly what we want to do. So before there was a residue, but remember the residue was just going by iteration. So when you exponentiate, you get rid of the residue. So I hope you believe me with that, like I can give you further support, but essentially you don't need anymore like to do you need to only do analytic continuation of this kernel, as we'll see soon. So how does it happen?
I asked a question
yeah.
on the previous, the one before actually.
Yeah.
Oh, actually, one even before that. So here you have everything phrased in terms of PA, PB.
Yeah.
Oh, okay. Could you go next? Yeah, slide 19.
Yeah, I use this effective HEFT version of classical.
So I'm just saying that in the pictures you have P1 and P1 prime, right? P2, P2 prime. So is there a subtlety between is P1 equal to PA? Or?
No, it's not. It's shifted. This definition that I had over here.
It's shifted by half.
Yeah.
Of transfer momentum.
It's written like this, PA and PB. Sorry, I should emphasize more. But it's this definition.
Right. So this is important for this setup.
Yeah,
like,
it's important.
Would something go wrong if you forgot that half of Q?
Well, so indeed, so if you forgot that, essentially I think there's still an exponentiation, but it's more tricky to show because you don't get, so what happens is that the subtractions that you do, the subtraction iterations are different in the Iconal approach without the shift things, which is done in a different way, as I said, that compared to this case in the heavy particle effective theory approach. So in particular, this relation is exact because this was a convolution. So convolution is a mathematical property. The transform of convolution is a product. So it's a simple mathematical property, and you want this to happen exactly. And this might go wrong if you shift in a different way.
So is it just because the delta functions you want for them to be exactly equal?
Exactly.
And if there's this Q squared sitting there, then it creates problems.
Exactly. Yeah.
So is there any tension with KMOC that you started with?
No, I don't think there is a tension. So it's true. I justify using KMOC, and then now I'm going to this, but I think it's just a way. You should think probably also in KMOC as parameterizing with this variable, probably.
Yeah, but the subtlety is important. That's what.
Yeah, it is.
Sure.
Yeah. But you can look at higher order calculation, 3PM, or the Iconal versus what they call like an operator, this exponential operator, or what we have here, and the subtraction is slightly different. But then it works anyway. It works anyway.
Okay. Thanks.
Yeah, for the exponentiation. Thanks for the question. Yeah. Okay. Right. So I do have up to 15 minutes, right? Yeah. I'll take. Can I? Or do I need 5 minutes of questions at the end? I forgot that.
Well, we don't have very strict rules. Yeah, you can have 5 minutes.
Okay. Because I was counting to do up to the what is 7 p.m. Russian time. Okay. So great. So we now want to do the analytic continuation. So look at these properties, these functions of the energy and duality continuation. Okay, it's non-trivial. You see there are square roots, so it's actually non-trivial in general. And one interesting point is that there is a connection, natural connection of this kernel with what is called Hamilton-Jacobi action, or in particular the radial action. If you want, the reason for this is that essentially we are using some WKB type approach. So in WKB, you will have some, exponential I over h bar, some type of WKB action. And essentially, this is what it's the analog of that for quantum field theory and the two-body problem. So it's the analog of that. And what happens here is that because we have a simple dynamics determined by these conserved quantities, like, and as I said, we are on the plane, what happens is that you have a simple function of the radial action. And remember that, as I was saying before, like when you have an Hamiltonian, right? So the differential equations are the same for scattering and bound, and only the boundary conditions are changing. So the fact that you can relate what I had before with an integral where you have the boundary condition in the integral means that you can try to relate the boundary, the contour of integration, okay? So this relation anyway between amplitudes and actions is called amplitude-action relation, or that's at least one in the names that we call. And that's one of the keys to try to then connect observables, because the actions are something that they are very easy, like are some generating function of observables, right? So here we kind of somehow we extract from the amplitude, we go back to the action, but now this is a compact two-body actions, okay, in terms of these quantities. Okay, so one of the interesting things is that there is a remarkable analytic continuation between scattering bound planar orbits. So as I was saying, looking at what we had before, so we have this relation between the kernel, okay, in my conjugate space in terms of my radial action, essentially. And the PR here is the same for scattering and bound. It depends if you want in a quadratic way of this P infinity square. So the only thing that can change when doing analytic continuation, this P infinity is supposed to pick up a factor of I, right, or plus I or minus I. So it's it will change either if you go to the bound state, this will always become minus P infinity, depending on the not depending on the branch cuts. But for the boundary condition, this radial roots. So this you have to think as some kind of turning point of the motion. So you have some scattering, you have some turning point of the motion, and then you want to relate this turning point of the motion, this kind of motion, okay? So this is the turning point, to some the radial roots of the ellipse, so of this kind of bound motion. It turns out that you can do that, and the two things are related, and you can find a simple answer for the radial action that is the one shown here for bound orbits in terms of the work for scattering orbits, which is just given by this analytic continuation, where the two branch cuts in this rapidity variable, essentially, you have to analytically continue both with the plus sign and minus sign. And in this emitter copy picture, we're always at 4 points, still in conservative case, we can still compute observables. So scattering angle and periastral advance, which are famous observables like in GR, classical scattering setup. Sorry, the scattering angle, scattering setup for scattering angle and bound setup for periastral advance are just given by derivative over the angular momentum. So it's clearly nice to have directly this radial action structure, because then you can just take derivatives and compute observables. I'm not going to go much into that, but can extend this for analyzing spin particles, and also for processing generic orbits. We're interested in radiation, so I want to now go to the bound waveform case. But this was a 4-point conservative motion. Any questions before I go to waveform case?
Well, I wanted to ask something.
Yeah.
Well, as I understood, eventually, well, at the beginning at least, you said that you start by computing, let's say, the S matrix in quantum field theory. But then, I don't know, what's the difference between the, let's say, scattering setup and the bound state setup? So to me, I would say that you would still have to compute for, if you want to address the scattering issues, you would still have to compute the same set of diagrams, right? But you would have to consider them in a different regime.
Correct. It's almost true, except that there are some contribution, turns out, which depends on the entire history of the trajectory, which are like tail contributions. And somehow this no local contribution, which depends on entire history, will not allow this simple manipulation for all the contribution at all higher orders. For QAD, it will be fine. Classical electrodynamics, this picture I'm giving is exact, and I think it's all order exact. But for gravity, at some point you have to change the tools, and maybe I'll comment on that later.
Thank you.
So it's that exactly that analytic continuation in the complex kinematic regime beyond the scattering kinematics, but there is some subtlety on the bound case. Sorry, on the gravity case, because of some effects that depend on the entire trajectory, which are not of this type essentially. Yeah. Thanks for the question. Okay, so very quickly, so you can generalize Swinger-Dyson equation to radiation. You essentially dress your recursion relation with a graviton. You apply the same symmetrization procedure, and you find some recursion relation. It is not surprised that also here you can solve it by going to hyperparameter space. This hyperparameter space is essentially the analog of partial wave basis that I was describing earlier for the Coulomb case. So long story short, you find some representation of the S matrix here on the left in terms of some exponential of the classical kernel. This is in this conjugate space. Exponential of the classical kernel times an exponential of essentially a coherent state operator, where this you have this new kernel, which is essentially given radiation. Okay, so these are two massive particle irreducible diagrams addressed with external radiation. This is still a conjectural thing, but it works. It has been checked up to I think 3 loops, and it seems to work. So as I said, this is essentially generalization of WKB approximation to S matrix, okay, for the entire quantum field theory two-body setup. Of course, we have learned that these are generating functional observables. So now you can go beyond what is natural Hamilton-Jacobi. You consider something like the waveform, which actually depends on this kernel here. Remember, it depends on the 5 points. So all the scattering bound observable can be derived with this gauging variable representation with the 2 MPI kernels. Yeah, I'm not going to show this in detail, but yeah.
So, sorry, in this equation, you have on the left-hand side, it seems like you have just an amplitude, right?
It's a Fourier transform in conjugate space.
Yeah, but in the right, yes. But on the right-hand side, you have an operator, a dagger of K.
Yeah, I mean, S matrix, it becomes an operator when you have multi-particle states in general.
I'm confused. Isn't that just already
this is the S
scattering?
I mean, this is the S matrix. It's not like the S matrix bracket into a state.
It's not a scattering matrix element?
No, because then you will have to expand this thing, right? It's somehow the operator. I should have written probably differently, but it's somehow the operator, right? So
I thought that the upper stuff with K1 to Kn was a coherent state. So it's, a state, therefore you are computing a matrix element with that state as one of external states. Am I wrong?
Yeah, but I mean, this gets expanded, so you get many creation operator, many gravitons, right? So what I'm saying is that for any number of particles, you have this representation of S matrix. Then you can take the brackets and will depend on your K tilde and only on these 2 kernels. But in general, S matrix is an operator. It has to be promoted an operator. It's not anymore a phase like a 4-point. I don't know if I answered your question.
I just thought that the massless particles were already combined into a coherent state.
They are. That's why, yeah.
Yeah, but that's what I'm not getting. If they're coherent as a state, they're already a state, right? So and you are multiplying the S matrix by
I guess
the
you want me to act on vacuum on left and right, and that's what you want.
Oh, maybe that's all that I need. Yes.
Yeah, I think that's
what's implied. Yeah.
Yeah. I mean, that's a schematic representation, right? So, but I guess my point is that these things exponentiate like just like WKB.
Okay. Thanks.
Yeah, thanks for the question. No, very relevant. Yeah, I should have probably put it in a different way, but it was just to give you an understanding of more or less what is going on. Okay. So open problem, we have done analytic continuation of the conservative kernel, okay, the 4-point part. So we now have the 5-point part. That's the interesting part. That's the waveform. Okay, so following the linearized Schwarzschild case, remember we have something. So we have the exponential. We don't have the expansion. So we don't need to take residues. So because of that, like residues disappear, and following the linearized Schwarzschild case where there was this wave function, we propose this kind of analytic continuation, where the rest essentially your rapidity P tilde relation, the binding energy, it's it needs to be analytic continue with a single branch card prescription, okay, and that's what we propose. Can this be verified? The answer is yes, because we know that people have computed post-Newtonian waveforms, and what happens for post-Newtonian expansion is that essentially you go to a central mass frame and you compute the multipoles, and there is some sort of matching between the theory of infinity, essentially the theory, around the compact binary, in such a way that the multiple of the objects correspond to the multiple of the source. Sorry, the multiple of infinity corresponds to the multiple of the source. So what you can do is, you try to expand like this waveform in time domain. And you have to do some rescaling. It's technical, and you will get some coefficient on the right, which is just this expansion as low velocity. Okay. And the interesting part is these multiples in the center of mass frame, they can be computed independently from the relative motion, right? So as I said, example of the quadrupole formula. So we're going to actually look at that, like, and now, you can relate this analytic continuation with the quadrupole formula and get agreement. Essentially, that's the idea. So very quickly, it's not important, the details. There are some scattering bound relative trajectories, okay? So the bound one is essentially like the ellipse, so there is some cosine, some trigonometric function, and the scattering one is taken in parabola, so there is an hyperbolic cosine. And the two things are related to some analytic continuation with some ice factor, okay, which are very related to this analytic continuation in the energy I was describing earlier. Don't have time to explain this. Up to 1 p.m., this analytic continuation works between the orbital elements. And what we want to do here, so here we have some motion which is not described in terms of the time. So when you look at the Kepler problem, unless it's circular orbits, you will never have an explicit time dependence. The time appears to the Kepler equation. The Kepler equation relates the time with this eccentric anomaly, and so you will have to relate the time to you, and then back to the to your relative parameterization. Remember, it is a relative parameterization between the two bodies. So because of this, like what we do when perturbative expansion in amplitudes, we get an exact answer in terms of the time, right? So how does that happen? What happens is that to make contact with the post-Newtonian expansion, this expansion in coupling, we need to solve the Kepler equation expansion at large orbital angular momentum. The reason is that large orbital angular momentum, this J, is essentially, since this J is rescaled by G, is essentially a perturbative expansion in G. So when you expand in G, you actually are secretly solving this Kepler equation, perturbative, order by order, and you effectively linearize. Usually, this is a transcendental equation. So when there are, when there is a function like this V, and then the hyperbolic sign of V, this is a transcendental equation. So it means it has no closed form solution unless it's an infinite sum, like infinite sum of Bessel function, things like that. But if you linearize it with this kind of expansion that I'm proposing here, you can compute analytically the time dependence of the relative trajectory. Why it is important? Because I want to make contact with the time domain waveform, right? So time domain waveform is a function of time domain multipoles. And time domain multipoles, like the quadrupole, require this kind of calculation of the parameterization of the orbit. Okay, so see we're running low time. So the thing is, now we apply quadrupole formula. So this is just blindly the quadrupole formula. Okay, so you have the x, j, which are the relative trajectory. You compute it, and you get this. And this exactly matches the expansion of the PM3 level waveform. So this is for scattering, okay? Now we have a proposal for bound. And what we find is that the proposal indeed works. So we can check both at 3 level in the overlap with the PN expansion. And also independently, it turns out that this paper wrote by these guys, Juncker and Schaffer, in the 80s, they have results at 1 PN without any post-Minkowskian expansion. And although they didn't claim it, like it turns out that if you check with the results, you can also check the 1 PN. You can analytically continue the waveforms directly. Of course, they have their own Kepler equation. You have to analytically continue the Kepler equation as well with what I was saying before. And therefore, our map is dependently verified. Okay, so okay, you can use this. You can compute the bound waveform now for example 3 level, as I was saying. And you recover the bound multiples, and it looks like this. So if you look at this, like, it looks a bit disappointing, right? So on the left, we have the result that we had before, and now you just get a jump, but on imaginary parts. So essentially, you go to a regime which is kind of actually unphysical. It's large because what you're doing is doing large centricity expansion, and the bound motion is, eccentricity must be below 1. So these things, it needs to be resummed in perturbation theory. Otherwise, it doesn't reproduce the expected behavior. How do we know this, that it needs to be resummed? Well, basically, it's this Kepler equation I was saying before. So if you solve this exactly, you will find the oscillation. Okay, so this is for the bound. So you'll find some sign. This will give you oscillation in the bound waveform. So you need to perform a summation of perturbation theory. So a Newtonian level, I'm going to explain how it works. Why is the wave bound waveform here not periodic in time? Sorry. Questions or? Okay. I'm gonna go very quick because I don't want to take much of the time. So, what you need to do is to solve exactly Kepler equation, and then when you solve it exactly, like this will give you the expected results. So on the left you see a scattering orbit, and on the bound on the right you see a bound orbit. So once you resum the object that you have here on the right in perturbation theory by, for example, solving the Kepler equation without truncation, you will find the periodicity. Okay, I'm gonna skip the next part because this was the main anyway result. And okay, we can with some perturbative correction. It needs still to be studied lots more. Okay, this was a summary table on analytic continuation. It's exactly what I said before. We need to study these tail effects, which I'm not going to describe here, but there are some effects higher order depends on the trajectory. And this depends in a local way, the trajectory, and therefore they need to be tackled separately. So it's not so trivial, let's say. These maps are the easier one at lower level in perturbation theory, but they need to be supplemented with something else like a higher order. So they need to be at least, improved. Okay, I'm gonna conclude it here. That's just a summary table, and yeah, happy to take questions. Thanks a lot for listening.
Thank you. Are there any questions?
Can I ask the following question? You showed your result at the previous to last transparency slide, like this one, and this is kind of h of u, probably h of is a function of time if you register it.
Yeah. So it's the real part of h of.
Why doesn't it look like the registered signal? Like the registered signal looks like a sine, of course, because this is a wave, and this one it looks like severely distorted sine.
That's right. Yeah. I got this question also in another talk, and so it's nice. Yeah. So let me think more about this. So basically, you see here on the left. So you have a big jump. As I said, most of the energy is released during periastron in scattering. So when you analytically continue, you start with something where physically most of the energy is released during periastron, and so basically you still have some spikes in the bound case. So that's why it doesn't look like just a sine. Let me say like that.
So at different parameters, it will look like a sine.
I think it looks like a sine, but I think that also including higher order corrections will help to make it look more like oscillating like what it should, how it should. So here you see from the left. So basically, you really see. I mean, these are the two waveforms analytic continuous. So you see the function that at some point, it twisted this part here and just developed this kind of behavior. So it's essentially the reason is that you start with the left, so you have this big spike, and so it still starts oscillating, but you have to add higher order corrections, like to really make it look like really oscillating like the one in the beginning. And so of course this is all early stage. These methods were developed like very recently, and we're just scratching the surface of the calculation we can do. So it's still not we're still not at the level of phenomenology anytime soon with this, but some of these things can be imported in some models for phenomenology. That's what I'm saying.
Okay, thank you.
Yeah.
So what's the eccentricity of what's drawn here on the right?
Yeah. So I mean, for this, The eccentricity, I think usually I take order of 10, which is what is reliable for
So it is still pretty eccentric, right?
It's still pretty eccentric. So,
Yeah.
so some people are doing numerical simulation, for example, at Albert Einstein Institute, like on scattering waveforms. And to get agreement, they need order 10 eccentricity.
So do the waveforms look similar with that eccentricity?
Oh, sorry, which waveforms?
With
Yeah,
large...
numerical ones. Yeah, they look similar to the one on the left. Yeah.
Oh, okay. So it's not actually that
No,
unrealistic.
you need
for
order
large
10 of the eccentricity, because the eccentricity in Newtonian level is related also to the coupling or to the orbital momentum, angular momentum. And so you need that to be, the coupling to be small. The coupling is small, eccentricity is large. So you need, it's like a perturbation theory works well when the parameter in the coupling is 0.1. In the same way, here works well when eccentricity is order 10.
Yeah, by the way, in this slide, you have the same equation twice. I guess you meant...
Yeah, I should have made, I meant the, sorry, yes, thank you. It was this one, yeah.
And also, in this middle line, you have one of the tangent functions inverse is, well, they are both the same. The inverse tangent functions are the same, but I guess one of them is supposed to be hyperbolic. Right?
Yeah, let me check that. Yeah, yeah, thank you. Yeah.
Well, it's just...
It's right in the paper. It's correct in the paper, but yeah, I mean this one. Okay.
I guess it's just a typo. Yeah.
Yeah. Thanks.
Um,
Any other questions?
So could you comment on? So how is that? Where is the? So you're referring to a resummation in the eccentricity.
Yeah.
And then I'm not exactly seeing what you mean here. So
I mean solving this equation numerically, for example, exactly. So this is what is actually done at the moment. So if you look at the effective one-body waveforms, what they do, they can never solve for time because the equation is transcendental. So transcendental equation, as I said, you can give an infinite series, you can do truncation of modes, you can do a lot of things, but it's not exact. So in the same way here, I mean solving this equation exactly. So in this case, I plotted the numerical answer of the solving this, and then seeing the oscillations. I cannot solve it because it's transcendental, as I said, unless you use the infinite sums.
But you throw away the O of 1 over C.
Yeah, here is just, here I throw it away, yes.
Fair enough.
Yeah. It's just to show how the periodicity is recovered, because, if you claim that this is an analytical dimension of the wave, for me on the bottom right, it's pretty disappointing. And indeed, like, that's not what you should do.
It's very interesting. Yeah.
You need to go back to the physical regime of eccentricity lower than 1. So when you are to computing this with scattering, eccentricity is very, very large. So you lower your binding energy, and then at some point you go to non-physical, you go to something that looks unphysical, but is just unphysical because it needs resummation. This is a common effect that happens many times. I discover when you try to do perturbative calculation of something that is oscillating, for example. So yeah. Other questions?
Well, I have a naive question. So concerning, I think last of your plots. So do I understand correctly that this spike in amplitude refers to, let's say, a phase of the scattering when they are closer to each other?
Yeah, correct. Correct. So yeah, I mean, basically, most of the energy physically is released when the objects are very close to each other. Let's see where, yes. So these are the two bodies scattering. So these things are, when they are close here, that's most of the energy being released. So there's a spike. And of course, yes, you analytically continue. I mean, you start with a spike. So you need to, if the function needs to be analytic, so you need to essentially have higher order in perturbation theory to smooth that out, essentially.
What I want to say, even for bound dynamics, so for this process, if you have high eccentricity, you still have kind of different phases, right? At some phase they're closer to each other, at some phase they're further away from each other.
Sure, because it's very eccentric. Yeah, because it's very eccentric. Right. Yeah, that is also happening because it's very eccentric. Yes.
Okay, I had another question. So at the beginning, you mentioned that, well, the whole reason why you are doing this is that you want to employ some modern amplitude techniques.
Yeah.
So, like, at which place did you do that?
Yeah, this. So,
so just analyticity.
I mean, it's also, together with unitary for factorization. I mean, you can use it more. I mean, because I've been mostly focused, like in the past few years, developing the tools, but there are people doing also higher order calculation, which I'm not mentioning, but like one loop waveforms and things like that. And these things are used heavily in that kind of calculations, and also conservative ones. I think. Also, let me mention this: the type of integrals that appear are also the type of the ones that you use in collider physics. So you can use IBP reduction and differential equations to put that in some kind of canonical form. And so these are just some of the examples of the tools being used. As I said, I focus more on developing some of these techniques for the analytical automation, everything like than actually doing calculation at very high orders. But yeah, this is an example, for example, that we got. So using the properties of the S matrix.
You don't use anything like double copy or things like that?
No, double copy turns out to be so it's useful in some instances, but in some sense you don't need to use it to go to a higher order. It's useful to construct some of the integrals sometimes, but at least for the cutting edge calculations that are doing, for example, there was a paper today by the Berlin group, like on the 5 p.m. first order Salesforce, and they they don't use these tools, but they use like IVP reduction tools. So as I said, like linear algebra tools to simplify to simplify the system of integrals that appear. So you have some phase space integrals for the observables, and this phase space integral can be put in a canonical form and then given a differential equation. So that tools are being used a lot, and this was not used before in the GR literature that I know, at least. This is because we're making contact with point particles. Then you develop some kind of Feynman integrals in this kind of tools. Does that answer your question? Or
Okay. I also had another question. So at the beginning, you said that you use an approximation in which you were essentially ignoring the Schwarzschild radius compared to, let's say, like scattering, what's called impact parameter, right?
Yeah.
So does that mean that you're computing some sort of like a first term in some expansion in this B over RG or vice versa? Schwarzschild radius over B?
So yeah, you're definitely computing some terms, some expansion. I mean, this is, as I said, from traditional collider physics is similar to Regge limit. So I mean, it's a leading expansion in, if you want, in the Mandelstam case, T over S, this kind of T over S. So central mass energy very large, and the exchange momentum must be much smaller than the central mass energy. So it's definitely a leading order term in that expansion, if you want. And that's what you're asking, right?
Yeah. So yeah, also kind of what I had in mind that probably it's related to some like it's not related to Post-Minkowskian or Post-Newtonian. So these are completely different expansions. Or
they overlap, but it's true they are different expansions. But in some sense, there are three expansions. So there is this indeed the Post-Minkowskian, which is what we said before. So it's expansion in the coupling. You do like this. So it's just like gauge theory expansion in the coupling. And then you have Post-Newtonian, which in some sense is an expansion in velocity, small velocity over C. And but that has some overlap. Like here, we don't expand in velocity. So if you expand in velocity, you get some overlap with Post-Newtonian. We don't get all the post-Newtonian terms, but we get some of them in the perturbative expansion. You can also expand in the mass ratio, like the cell force, and you have yet another expansion. So I think all these tools are complementary, but they have overlapping regime of validity, if that's what you're asking, and you can check things, which is very useful.
Well, the thing that Mitya mentioned is more like an EFT expansion, whereas these are calculational expansions, right? Those are different expansions.
Sorry. Yeah, this is an FT expansion. What's the question again?
No, it's not a question. I'm just trying to help me to understand that you can compute an exact action perturbatively in G, right? In the coupling constant, and that's just a calculational expansion. Your perturbation theory is constructed in this way.
Yeah.
The actual action that you are computing, that for which you are computing, can also be an expansion because it's actually an EFT, not the full theory. No, barely anybody does full theory in the sense that we don't know how to compute full black holes. We only know how to compute point particles that have some EFT coefficients that correspond to black holes under some matching. And classical people also do EFTs because they do word line calculations, and by word line they mean point particles, classical point particles on the word line. So they also, in an EFT way, in an effective way, replace an extended object by a point particle, and that is a modeling expansion or an EFT expansion, which it's separate from your expansion in the coupling constant. But not unrelated, of course, because the size parameter of the black hole, it contains G in itself. So it's not entirely unrelated, but it's like conceptually very different, I think.
Mm-hmm.
Yeah, so there is no hope that like by summing very, very many terms, you will be able to kind of compute something related to this kind of collision phase. Not in spiral, but the one which is when they're close.
Good. Yeah. Well, I would say you can get, so there is some radius of convergence, and there is to the convergence, dictated by the fact that you're doing this expansion large distances. So at some point, in particular near what is called ISCO, innermost stable circular orbit, the perturbation theory will need, we need a resummation around that. But you cannot, so that's just going back. So you will need to stop at some point here and then trying to merge it with other tools. But this has been done in the same way in the post-Newtonian. So even post-Newtonian people, they develop a model which, trying to put together the part in the spiral and the part in the merger and the part in the ring down since the early stages. So so I think that's essentially the same spirit here. But indeed, the summation is important. You don't get non-perturbative effects. That's what you're asking, like near the merger. Those are not there. But yeah, this part is understood analytically. You can compare with models, right? So, and as I said, also it's very flexible, like that. Different type of effects, like curvature correction in GR, which are hard to study in the full GR. I mean, with a full classical perspective with actions. Here are just higher dimension operators, so you have some kind of classification of the type of effects that arise, at different orders, which make it easier to understand, like also the phenomenology in some sense. Although it has not been pushed so much yet, but I think in the future it will be. I don't know if this helps, but yeah.
Yeah, thank you. So do we have any other questions?
Maybe Mitya. Hi, Riccardo.
Hi.
Maybe just two quick points. I think that's a follow-up to what Alexander was asking about this eccentricity. So effectively, you are doing perturbative resummation to acquire the final result, or you are not actually solving, right?
So as I was saying to Alex, I think before, like here I'm solving numerically this equation for the plots because you cannot solve it analytically because it's an infinite series expansion. That's what you're asking?
Yeah.
Okay.
So, but you are not doing any perturbations and a follow-up resummation, right?
No, that needs to be done. That's what I'm saying here below. Yeah.
Yeah, so that's what I'm making precise. Okay, but do you think with this your bound waveforms you can also capture these tail effects, or it's not?
Not yet. So the tail effects arise in the next order, which is one loop or beyond 1 p.m. And essentially they are very subtle because I said it depending on local wave and trajectory, something that does not appear as I say in classical electrodynamics. So in classical electrodynamics, everything on this slide, I think it's correct to all order in perturbation theory, but in gravity it's not true because of this local in time tail effects. So what you have to do is to make more contact with trajectory. So here I'm doing analytic continuation at the level of observables. So the final result, I'm taking the final result as an analytic function of these variables, but these arise from some integration, right? And what actually is relevant at the level of a trajectory, you can compute bound and unbound separately. So if you have a better connection with the trajectory, of course, it's a gauge-dependent concept. So it's harder to do it here in this kind of framework. But perhaps there are techniques only to tackle this kind of. I mean, there was also a recent paper on 4 p.m. On Monday, I think, by Rafael Porto's group, doing exactly for some non-local in-time effects, although they sidestep some of the problems. But essentially, you want to have a better connection with the trajectory. So this, see here, yeah. So the kind of map between the trajectory kind of works also for these effects.
Somehow I thought you cannot. What is exactly happening? You cannot extract this analyticity data from your bound configuration or the S matrix.
So it's it's not clear that you cannot. No, this is not clear. So it's just basically you need some integration from the S matrix to the observable. In this integration step, you lose some information that might be relevant for these effects.
Okay, I see.
So I'm not, so you don't have only S matrix. We are talking about observable, so there is some integration to be done. And that integration might lose the information that we need for the non-local piece. Yeah. So I'm actually hopeful that something can be done at one loop.
Okay.
Yeah, was just our first. I mean, as I said, it's some preliminary investigations. Like there's still a lot to be done. Yeah.
Okay. Are there any more questions? Okay, good. We don't have any further questions. So thank you very much for a nice talk.
No, thanks to you. Thanks to you for the invitation. Like, thanks for everything. Okay. Thank you.
Thanks, Riccardo.
See you, Alex, Anton. See you, Dimitri.